This video is about something called z-scores and something called the normal model. This chapter is probably one of the most important chapters that we will study this year because it creates a foundation for the rest of the year. Okay, by the end of this video, you should be able to explain how shifting and rescaling data affects the measures of position and the measures of spread. You should be able to define z-scores and calculate a z-score when given data. You should be able to find percentiles when given a z-score and find a z-score when given a percentile. You should also be able to determine if a distribution is normal or not. So first, shifting and rescaling data. When we shift data, we are adding or subtracting a constant value to each data value. Okay, so if I take our GPA data from chapter 4, and we add 1 to each value, then we will find that the 5-number summary is all 1 number higher. Okay, those are all measures of position. The maximum, the minimum, Q1, Q3, those are all measures of position, and they all shift with the data, which kind of makes sense. Okay, but there has been no stretching of the data, it just was shifted up 1. And so the IQR did not change. Okay? In general, whenever you shift data, the measures of position will shift with that constant, but the measures of spread will not change. Okay, this is also true for the mean and the standard deviation. So the mean would be 1 number higher, but the standard deviation would not change. When we rescale data, we are stretching or shrinking it. Okay, we do that by multiplying or dividing a constant to each value. So if I take this data and I multiply each value by 2.5, then the 5-number summary would also stretch by being multiplied by that same constant. Okay, and because it's being stretched, hopefully it makes sense that the spread would also shift by that same amount. Okay, so in summary, all measures of position and all measures of spread will be multiplied or divided by that constant. Okay, now to kind of put these two ideas together about shifting and rescaling at the same time. Okay, this is the level of question that is on the AP exam. If we took our data set and shifted and rescaled it to match Switzerland's grading scale, a 1 to 6 grading scale, by multiplying by 1.25 and adding 1, how would this affect the measures of position and the measures of spread? Well, the 5-number summary, the measures of position would all shift and rescale by multiplying by 1.25 and adding 1. Okay, the IQR is a measure of spread, and so it would rescale but not shift. And so we would only multiply by 1.25 with the IQR. Okay, the same thing is true with the mean and the standard deviation. The mean would shift and rescale, but the standard deviation would only rescale. Okay, next topic. Now that we know how to shift and rescale data, what if we took 2 data sets, maybe even different types of data sets, and shifted and rescaled them to similar scales so we could compare them? Okay, what if there was a standard scale that we shifted and rescaled all data to so we could compare them? And the truth is there is a standard scale, that's not a technical term, but I'm just calling it that has a mean of 0 and a standard deviation of 1. Okay, and we can shift and rescale any data value or any data set to this scale by using this formula. Okay, this is a super important formula in this class. You should memorize it right now because we will use it frequently throughout the year. Okay? These standardized values that we get from this are called z-scores. So here's an example that uses z-scores. Okay? So we're comparing two track athletes and comparing their long jump and shot put scores compared with the mean and standard deviations. Okay, and this type of calculation actually happens in things like decathlons and triathlons and things where multiple events are happening and you have to find one winner. Okay, so the question is, who is the better overall athlete? Is it Kluft or Sklut? I can't say those names, I'm sorry. Okay, so we can do that by finding the z-score for each athlete in each event. Okay, so we would take their score and subtract the mean and divide by the standard deviation and get their z-score. Okay, for each event, and then in order to compare them, we could then add up their z-scores and find out who has the better overall score. Okay, that's the way we can compare, two athletes in two different events by using z-scores. Okay, the z-score of a data value is the number of standard deviations above or below the mean that data value is. Okay, so for example, Kluft's long jump was 2.7 standard deviations above the mean, and Sklut's shot put was 2.51 standard deviations above the mean. Okay, so the z-score is the number of standard deviations above or below the mean a data value is. Okay, and I hope it makes sense that a negative z-score would be below the mean. There's no example here that I could pull from, but that's also true. Now, let's talk about another way to use z-scores. Now that we are shifting and rescaling data onto a standard scale, we should also talk about the fact that a lot of data naturally follows this distribution. It is called the standard normal model or the standard normal distribution. If you found life expectancy, if you looked at heights in a very large population, if you looked at most variables in a large population, you will find that the data naturally tends to follow a standard normal distribution. Okay, so that's a very useful model for us to use when looking at percentiles or other data. Okay, before we use this model, however, we must check that our data is roughly symmetric and unimodal, so it makes sense to use a bell-shaped curve like this. Okay, if it is, then we can find percentiles. But first, let's talk about a rule of thumb. Okay, on the normal curve, 68% of data is within one standard deviation from the mean. 95% of data is within two standard deviations from the mean, and the 99.7% of data is within three standard deviations from the mean. This is called the 68, 95, or 99.7 rule, or it's also called the empirical rule. Okay, this rule of thumb to get an idea of how much data is within one, two, or three standard deviations of the mean. Okay, but if we wanted a more exact percentile, okay, we could use either the z-table as found in the back of our textbook or will be given to AP students on the day of the AP exam. Or you can use your calculator. Most students tend to use their calculator, but you can use either one. Okay, if we had a data value that had a z-score of 1.8, okay, we could look on a z-table, look at 1.8, and then the hundredths place was 0, and that would give us right here the place on the table to look of 0.9641. Okay, so a z-score of 1.8 has a percentile of 96th percentile. Okay, on the calculator, if you hit second and then vars, which is kind of over by the arrow buttons. It's labeled distr, or for distribution in blue, and you pick number 2. It says normal CDF, the normal cumulative density function, and then you type in left bound and right bound. That will give you the amount of area under that curve. Okay, so I need to go off to infinity, and so I type in this, a really very small number, -9999, comma 1.8, and it would give me the same value, the same percentile of 96th percentile. We could also take this and go the other way. So I could go from a percentile to finding a z-score going the other direction. Okay, so if I wanted to know the z-score for the 90th percentile, I could then go find a number on the table that's close to 0.9 and then find that it is 1.28. It has a z-score of 1.28. Okay, on the calculator, I have to use a different function to go the other way. Okay, and it's number 3, inv-norm, on that same distribution menu. Number 3 is inv-norm, or the inverse norm, and you type in the percentile, and it will give you the same z-score of 1.28. Okay, we would then have to convert that z-score back into the same scale that we got the data from for it to be meaningful to us. Okay, that's how you convert from z-scores to percentiles and from percentiles to z-scores. Okay, the last topic is something called the nearly normal condition. Okay, as I mentioned before you can use the standard normal model, you must check that the data is roughly symmetric and unimodal. Okay, this is called the nearly normal condition, and you must check this before you use the normal model. Okay, so you can check on a histogram to see if it's symmetric and unimodal, or you can use what's called a normal probability plot found in StatPlot on your calculator. Okay, this plot will graph each data point with its z-score. Okay, if the graph looks roughly straight, which this looks roughly straight, then it is nearly normal. And you can see that over here in the graph that it is symmetric and unimodal. Okay, if it is not straight, this one looks pretty curved. Okay, and we can see that in the histogram because it is skewed to the right. Okay, or it's skewed to the higher values. Okay, so that's a normal probability plot, one way of checking to see if our data is nearly normal. So this video was about z-scores and the normal model. I'm hoping that you're now more familiar with shifting and rescaling data and how that affects measures of position and measures of spread. You should also be able to define z-scores and use z-scores to find percentiles and also determine if a distribution is normal or not. Thank you for watching.